Here you have a recipe to calculate the residue of a single pole without explicitly expanding a function in the Laurent series. So what you should do is take that function, multiply it by z minus z naught, and then evaluating that whole thing, perhaps even taking the limit of z going towards z naught. So just pause the video to think how you would solve this, obviously making use of the Laurent series expansion. So work that out, and then we'll come back after the break. Right, so we know we're dealing here with a single pole. So in that particular case, we can more or less write down the Laurent series, or at least the general form of it. So the Laurent series around the point of interest, which is z naught for a single pole, looks something like this. We have f of z is, and then the first term that will appear is a minus 1 over z minus z naught. And this is the first term that will appear simply because we have a single pole. Otherwise, we would have more negative powers of z here, but that's not the case. And then the next one is a naught, and then we will have a 1, z minus z naught, and so on and so forth. So what are we interested in? We're interested in a sub 1 here, because that coefficient is actually the residue. So this is what we should recover. So let's see if we can recover that using our recipe. So the recipe just told us that the first thing to do was multiplying our function by z minus z naught. So then we get a minus 1, a naught, z minus z naught, a 1, z minus z naught squared, and a lot of higher order terms. And yeah, that's basically already where we need to be, because you clearly see that if you evaluate the results in the point z naught, that all of these higher order terms will vanish, and the only thing that's left is a1. And that's exactly what we need here. So with this particular residue, with this particular formula, you can calculate the residue of a single pole without needing to calculate that Laurent series explicitly.